am about to submit my thesis. I am working in the field of robotics, where I learned basically dynamic controllers, then kinematic controllers to control robot motions. So, this talk is about how robot can learn through imitating others motions. Well, this talk is interactive. You can interrupt me whenever you feel. Well, first I will introduce about what imitation learning is. I mean, how imitation learning can be used to learn robots motion. Then I will go to how this imitation learning approaches can be applied to robot learning through learning stable robotic motions through demonstrations. So, demonstrations are basically what we show to the robot, and that is how the robot learns by seeing that demonstration. Then we will talk about how multitasking profiles can be incorporated in a model. Then I will talk about an application where we teach the robot how to pick and place objects in automated warehouse, right. Then I will conclude. I hope the time will permit. Anyways, so this is a learning control architecture of a robotic system, where this is our robot, and the robot generally work in the Cartesian workspace, right. When we place pick one object, we do it in the Cartesian space. So, similarly robot also works in that way, but the robot motion is actually controlled in the joint space, right. And this joint movement of this joint space is controlled by a control torque, that is u, which is designed or which is calculated using a controller, which is a dynamic controller, which involves robot's dynamics. And this comes, so basically what we do, we direct the robot in the Cartesian space where to go, and using that desired position or orientation command, we compute the inverse kinematics. So, inverse kinematics is basically the desired joint positions of the robot, which is fed to the controller, and the control input is generated, and again from the robot joint position we compute the forward kinematics, which is basically the position and orientation in the Cartesian space. So, our job here, so what I will talk about here is basically the design of a kinematic controller. So, there will be using imitation learning. Well, mammals, skills in mammals are not generally hard coded in their brain, right. We learn it when you grow up. So, when a child takes birth, he or she knows how to move a hand, but he or she cannot do it precisely. So, eventually we learn it, right. So, the child, when the child learns, what he or she does is, sometimes what she does is that he minimize a performance index to improve his or her motion, and then he gradually learns a motion, or a child can mimic others motion like the elders doing, and he or she mimics it. So, what is imitation learning? I'll show one video here first. It's a clip you might have seen before. Okay. So, this is a clip from a movie Real Steel. Is it visible? Okay. See, the human here is basically showing how to move hands while the boxing or something fighting, right, and the robot simply mimics it. So, this kind of motion you cannot simply program, right. You have to have some algorithm which can simply reproduce this kind of motions, right. Fine. So, what is imitation learning? So, how to learn or to imitate human actions, or we develop skills by watching people, like when we go to when we start playing table tennis. So, we gradually learn by seeing others how they are playing, right. So, we improve skills by imitating others. So, these are the motivations behind imitation learning. And see how here, sorry, yeah, how the player is performing, seeing the player, the robot is trying to imitate that particular motion. So, this is about imitation learning. Why it is required? Because as I have already shown that when there are complex motions involved, like we cannot directly program it, we need to have some mechanism that can encode that motion. So, that is why we require imitation learning. These robots are generally pre-programmed, where I will show that during motion planning, the existing approaches are generally they are pre-programmed. Robotic scientist, what he does is he programs everything how to move in a Cartesian space, and this way the robot moves, but this kind of motions are not generalized enough, right. So, in a unstructured environment, this is very difficult to execute such motions, because there are uncertainties involved which may not that will cause disturbance to the robot motion planning. Application areas are here.
So, how that algorithm is fitted? Just by encoding different positions, and then you said the imitating that mimics.
Yeah, so that will come to that point, because we are not simply fitting that well, go to that position, it's not like that, because that is a repetitive motion. When I simply encode that robot moves from here and here and here, and then I try to generalize it, I cannot perform that motion at the other location in the workspace, right, because that location of that region of the workspace is not programmed in the robot. So, robot will be simply fail in that scenario, right, or something like you have pre-programmed your motion planning and an obstacle comes in between, the robot cannot, that will definitely collide, right, because it is following the code blindly, it is not taking any feedback. So, that is why we need some mechanism that can incorporate that decision making capability. So, I will eventually come to that. So, these are the application areas. So, this is about warehouse automation, where see here a robot is employed here instead of a human, that will do the pick and place task, like when order is placed, that will go to the robot, and the manipulator on top of it, that will reach to the rack and that will pick the particular product and place it. Then in car industries, in domestic applications, like now we are thinking, especially in western countries, manpower is a very dominant problem, right. So, there now we are thinking that this can be replaced by robots who can perform domestic tasks. And again in healthcare, so that is also a very big area, where in industrial robots, then space applications and entertainment as well. These are the areas, and well, in competition you will see that have you seen Robocop in YouTube? So, you will find that this kind of robots, these now robots will be playing football and all that. Okay. So, these are the application areas. Well, so motion planning approaches. What are the available approaches? So, what is actually motion planning here? The robot is commanded to go from place A to place B. Now, you need to have an algorithm in a suppose it is a structured environment, you know where the obstacles are, right. So, the motion planner, what it does is it creates an path by maybe interpolating points, it will find a path from A to B, then so that comes under path planning. Then you will have some classical control technique algorithm, so that will generate instantaneous commanded instantaneous velocity commands that will be needed to track this path, right. So, classical approaches generally goes by they go by two steps. First is motion planning, then they will track the trajectory, and in order to track the trajectory they will come up with velocity commands. So, that you will use where classical control theories can be used, but these things never never took care that what are the environmental feedback that should be there in the motion planner. So, these approaches did not work well. Then people came up with this sampling based approaches, where probabilistic roadmap was popular, where in a suppose this is your environment where these are the free spaces, and based on the probability of the free spaces, initially a global planner that will sample the workspace, and then connected graph will be created, and when a query comes up like here a start point, and the robot needs to go to the goal points. So, it will take a graph based search and calculate a path from start to goal, and it will work out. But these approaches are computationally expensive, right. You need to search the total global workspace, right. Then rapidly exploring random tree, this is also an sampling based approach, where what happens from the start position, it randomly creates points in the workspace, and what happens is it creates a tree, and until it reaches the goal. Then when it finds the goal, or maybe in the confined region in the goal, the planner is said, well, I have reached here, then it creates the shortest path from the goal to here, and the path is created. But still they did not incorporate the feedback here. So, what is happening inside it, it did not know. Then comes feedback based approaches, where potential field was very popular, where what happens is this is a workspace, right. So, this is a 3D workspace, and this has been represented as a potential field function, where this is, suppose this is your goal, and this is a attractor here, and these are repellers. So, if a motion starts from here, so it will the repeller will push the motion outwards, and eventually it will reach the goal, right. But here see it will find one way, but it's the human skill, the expert skill are not transferred in the motion planner. It will go by the how the function is defined, and again in potential field approaches there are problems or local minima. So, it might stuck in local minima, and to deal with this local minima problem, then people propose navigation function based approaches, but well, it's good, but problem is that unique navigation, finding an unique navigation function is difficult, right. Then people came up with regional approaches, where region wise a funnel like function was discovered to describe the motion. Our motion starts here, and due to this funnel like function, the motion reaches here, then again another funnel starts, and it also pushes the trajectory towards the end of it. Eventually it reaches the goal, and so these are the approaches which took care of feedback of the environment. But the problem is they didn't they are not efficient enough to incorporate skills from the human expert, right. Like when we take lessons from our gurus, right, in maybe in sports and all, we see people how they are playing, how they are taking a shot to a particular, maybe a soccer or maybe in badminton. We learn it, but this kind of approaches couldn't do that, right. It's more planned in a sense that, well, you have a function that can decide based on the instantaneous feedback, but problem is that function is not designed to take care of what kind of motion is intended. it's planned in the known space, that's true. It can be incorporated in the unstructured environment as well, but the problem is that you do not have the control over the dynamics of the system, right. So, it will go by as the dynamics of the function is defined. Okay. So, I will show an example how it works. So, then people propose dynamical system based approaches, right. So, here the idea is a motion is described in the form of a differential equation, where this x dot may be the Cartesian space velocity, and this is a function, nonlinear function, that representing the trajectory. So, when it unfolds, when this function unfolds in time, it will create a trajectory. Now, suppose for this moment somehow we have learned that this f x can be represented by x. So, x dot is x, right. Now, if we choose a x as negative definite, the system is asymptotically stable, right. So, when the system is asymptotically stable, and if we suppose for a particular set of parameters we evolve the system, the system unfolds in time and we get this kind of response, fine. So, the state starts over here, suppose this is the norm of the state. So, norm of the state starts over here and it eventually reaches to 0 as the system is asymptotically stable. Now, for another set of A that is also negative definite, the response will change, right. Suppose this response is like this. Now, suppose this is your, this represents suppose in 1D the motion of the end effector, right, how the end effector of the robot is moving in the workspace. So, if we say that, if we say this is our motion planner and at each instant we say what is the commanded velocity and the position at the next instant will be calculated from that velocity and we will tell the robot go to that position, right. That is how it goes. So, for its particular set of A will have different kind of trajectories, right.
How is it working n-dimensional space? This is only for one-dimensional space, right?
No, I am saying suppose it is in one dimension. So see here x is a vector, it is a bold symbol, right. So, it is in n dimensional. I have plotted the norm of the state here. So, that is why it looks like in one dimension. So, I am simply showing how the norm is changing. So, now see, now our life is now easier, right. We have a function that can tell that what is the trajectory would be or what is the instantaneous position at each sampling instant, right. Now, if we have a inverse mapping, if we can learn the inverse function, like I have told the robot that, well, this kind of path you have to follow, and for that you learn your A so that this thing fits. So, that is our problem. So, we learn the inverse mapping here, right. So, we learn the parameter of the motion planners so that it can act as we want. So, now see, the skill is already there. So, I show the robot that, well, move like this. I look at the laser pointer. I show the robot that move like this, right, move like this, and it records all the position, and from that it learns the parameter so that this motion is this motion can be created using this particular model. Clear? So, that is our problem here. Now, this is a simple linear system and we cannot generalize it. So, we can every time if you start with any x, so it will create this kind of motion. So, we need to have we need to parameterize the model so that this kind of generalization can be there, right. So now we have two problems here. First, that we have to learn the mapping precisely, so that the exact trajectory is encoded. Next, which is more important, that is about stability of the model. Here I have defined that A is negative definite. If when we are learning the inverse mapping, we do not have the control how the parameter, I mean how the structure of the A would be, right. So it can be positive definite, it can be undefined, right. So in that case, this trajectory what starts from here, it will never reach to the 0. Well, at least we cannot ensure that it will reach to equilibrium. It might overshoot from any place, right, because it is not stable, the system is not stable. Any doubt here?
System is stable, right? Why it is unstable?
It is unstable because A is not negative. Suppose if you have a, so to analyze the stability of this system, suppose I take a Lyapunov function, that is V equal to x transpose P x, fine. Are you familiar with this? I think you are familiar with this, right. So this is a, suppose this is the energy of the system, right. So the system is stable when energy is gradually decaying to 0, then only say the system is stable. If the energy of the system is gradually increasing or it is never reaching to 0, the system is never stable, right. It is like as it is in oscillator, it keeps on oscillating. So now if I calculate the V dot, the change of the energy, so that is x transpose P, that is x dot, so A x plus, it will come around, so if you change the transpose again, so it will come like this, x transpose A transpose P x. So basically it will come like P A plus A transpose P, okay. Is it fine? So now see, if this term is negative, sorry, okay. So if this term is negative, this V dot will always be negative. If it is not, suppose it is 0, it will be 0. If it is positive, V dot will always be positive. If it is undefined, we cannot say anything about V dot. So that is why I say when A is negative, the system is stable. When A is positive, the system is unstable. Even if A is not defined, what A, the sign of A, we cannot say anything about the system, right. So okay, so that is why I told that the most important problem is whether the system is stable or not, right. So now we need to figure out how can we learn that parameter while keeping the system stable, right. So here research, our research problems are divided in two parts. First is learning the parameters, how accurately we can learn the parameter, and then whether it is stable or not, right. Well, in imitation learning approaches, this can be of two types. One is symbolic encoding, like symbolic encoding is what task we are performing, and robot is expected to reproduce that task. So that is symbolic encoding, and the trajectory encoding where the robot learns the trajectory. So the task is not that much important, rather the trajectory is. And in symbolic encoding is not is much of use in especially in some cases, but trajectory in encoding is quite applicable. So, we concentrate on this part where trajectory encoding, two popular methods are dynamic movement primitives and encoding using Gaussian mixtures. So, in dynamic movement primitive, it is assumed that a motion can be encoded using a function like this. So, our assumption is, suppose we show this kind of trajectory to the robot. So, this is my start, this is my goal. We show this kind of trajectory to the robot, and we expect or we assume that this response can be encoded using this function. Now, as the stability is the issue, then what dynamic movement primitive does is, it learns the dynamics as this, right. So, here I have shown second order dynamics here, I have taken y double dot. So, it can be like you can change the state space, you know that, right. So, it is represented as a combination of a PD controller and a force at a nonlinear function. So, PD controller, if we change if we select this gain precisely or with our expertise, we can make a stable system using a PD controller, right. And now, we have a forcing function, a nonlinear function that takes care of this thing, how this trajectory is moving. It learns how the features of the trajectory inside it, and how it is defined. It defined like this. So, this system is actually driven by this state, which is defined as this, and this is called canonical system. So, see here, this canonical system is always asymptotically stable if A is positive, right. If A is positive, then it will be always stable. And so, I will show how Z changes. So, what we do is, we take the trajectory of Z and we kernelize it, and we learn the function, the forcing function, so that this whole system can represent this kind of motion. Okay. So, now see, now this whole function is basically this one, this pi of x comma w, where x is the state and w is the parameters of this function. So, we learn this system in this way, and where this forcing function is defined as this, it is a combination of local models, right. So, and this is the firing of these local models. So, now, if we look at this response of this Z, so as it is a asymptotically stable system, the Z starts from here and it exponentially decays to 0, right. So, what we do is, we take Gaussian functions and we kernelize it, and based on that, this function f is learned, so that this whole function matches this trajectory. Now, the problem is here, when Z is exponential, if we map it over time, we see that in the time domain, the Gaussian kernels were placed at similar intervals, but when it is transferred back to Z domain, all the kernels are they are collapsed over at the end, because the length of in time is greater in this region. So, it is better we find good response when you use a linear the z, and we do it in time scale, and when it is transferred back to the canonical system space, so then also the similarity is there.
So what is the Gaussian kernel? Like, doesn't make sense.
Sorry,
What is the Gaussian kernel? What is the kernel? What is kernel?
Gaussian function, it's a Gaussian. So basically what we do is, instead of making it a crisp value, we take that where at this instant of time, what is the firing strength of the model. So we are considering local models, right? Suppose I have this kind of trajectory, and I have learned a system like this, a system like this, system like this, right? So basically this kernels decides when this system will, like I have already told that x dot equal to ax. Suppose this is your that local model. So now I am taking combination of all the local models, and I am giving the global response.
So I will have one A for every one function for one kernel.
Exactly, A for its representative, not exactly A. We have I will show the form, but this is the idea behind it. We combine all the local models and generate the global response, and this basically this kernel, the psi, that will give you the weight of this kernel, how much the local model is fired. So based on the combination, will generate the response, and that will give my model. Yeah.
What do you mean by fired? Like what is
Fired means suppose
it's like a force which is
just I am drawing this model over here, right? This is my model, right, and this is the center of my model, right. Now at time, when the time is here, I am at the end of this model, right. So rather than if another model was like this, which was close to this its center, so weightage of this model was greater than this one. So firing means which model is more active in that region. So that is about firing, and this C is basically this centers, right, and here H is the it's sort of variance of that Gaussian kernel, right. Okay. So well, dynamic movement primitive have they have applications, good applications in especially in playing playing table tennis and all. But the problem is dynamic movement primitives, they learn in single dimension, they do not incorporate the correlation between among states. So it's learned in one dimension. So for each dimension there will be one movement primitive. And so when you were learning DMP is for robot, DMPs are dynamic movement primitives. So what you do is you learn it in joint space. So you try to capture how the joint space trajectories were demonstrated, and you learn that motion. But and it has a time dependency, as I showed using that canonical system. So it always goes from 1 to 0, and based on that, so the time it takes from during the demonstration, all the motion has to be completed within that time framework. So DMPs has these limitations, and another thing is it will exaggerate the motion. Suppose when you try to scale the motion up or down, it exaggerates. Like when we are scaling up, it creates a huge big motion, then when we are scaling it down, it creates very small motion. So to tackle that, but in Gaussian based approaches, this problem is tackled. So in Gaussian, well, another thing I forgot to tell, that this function, so this nonlinear function, you can use any nonlinear function approximation technique, like in neural networks. Then you can use also Gaussian mixture, the Gaussian mixture regression. Then LWPR you can use. Then any deep learning techniques you can use. So this, yeah, but linear regression will not give you that much of, because it's a nonlinear function, right? So you will have a particular type of motion, but that will not be generalized enough. So it's better to select good nonlinear function approximation techniques. So deep learning will do well. Okay. So in in Gaussian mixture based approaches, the system is defined as earlier like this, and the Gaussian mixture model, it learns this function fx, right. So, Gaussian mixture regression, what we do is, we have a data set where we have demonstrated the robot, this is the position and this is the velocity of the robot at each instant. Suppose we have given d number of demonstrations, and at each demonstration ni number of samples are there, right. So, from that we learn a joint probability of this data set. So, once we have that joint probability, well, we learn this joint probability using expectation maximization. So, once we learn the joint probability, we can simply regress it to have the regression model where fx will represent the x dot that I have already shown, and this comes from the joint probability distribution, where this is the mean of the kth Gaussian, and these are the variance of kth Gaussian, right. So, again the problem is about stability, because when we have learned in dynamic in DMPs, that was stable because of the PD controller, but here no such model is there. So, that is why you have to ensure that this fx is stable, right. So, what people do is, if you rearrange it, you can write it in this form, ak equal to this and bk equal to this, where the x dot model can be represented in this form, where this k is number of Gaussians are there in the mixture model, right. Suppose this is your demonstration and you have learnt a model like this. So, you have used here 5 Gaussians, one here, one here, one here, one here and one here, and the center and variance of the Gaussians were discovered using the expectation maximization algorithm. So, now to make the system stable, what that particular approach does is, it makes the system first this term, they makes it negative definite, as I have already shown during the Lyapunov function analysis, how the system is stable. In that way, when they are learning the a parameter, they making it stable, they ensuring that this term is always negative definite, and at x star, when it reaches x star, they make sure that this term, which works as a disturbance to the model, which is also 0. So, what happens when the trajectory during reproduction, it reaches over here, it reaches x star. So, this term becomes 0 and the x dot is equal to 0. If it is 0, then the response will be 0, and the velocity, as the velocity is the 0, the system will not move, it will stand still there. So, that means our system is stable. So, that is the approach has been taken over here, but problem here again.
So, x star
Yeah.
is the desired
Target point, exactly.
and we will have one a value for every one desired x star, right?
No, x star is fixed.
Oh, that is the one that final value which you want, right? Okay.
Suppose this black squares are your sampling points, right. You have sampled the demonstration, and this is your start point and this is your x star, right. So, for a k and b k are related to each Gaussian, these are the Gaussians, right. I have 5 Gaussians.
Yeah.
So, this a k and b k are related to this models, right. I have one x star and this many a k's and b k's.
So, we will have one a k and b k for every Gaussian, but we will have only one x star for the entire model.
Yeah, exactly, because you have a fixed target point, right. When you are demonstrating the motion, you are reaching the robot to a particular point. Well, but well, this model is good, but the problem is what happens is that this particular constraint it doesn't care about what is the natural Lyapunov function of a system. So, it simply force the identity Lyapunov function to the system, and again it's not generalized in a sense that when your x star changes, you try to reproduce the motion for a different x star, the model fails, because this model is only stable for this x star. Fine. So, because AK and BK are they are fixed, but they are changing in a sense that when the system is operating over here, this HK will have certain value, right. When the trajectory changes a bit, HK will again change, because HK is basically the Gaussian membership function. Yeah, right. You got that, right. So, this model is not well generalized. So, that is why then we dig into the problem and then we propose this thing. So, we learn the motion using stable movement primitives, like so primitives is basically this local models are called primitive. So, you learn segment of motions and you combine all the motions, you generate the global motion. So, that is how primitive based modeling is modeling works. So, we propose our model in this way, where x dot is represented like this. So, to make this system stable globally, we add this term, right. So, this is our control term, which will drive the system to the equilibrium point or the target point, and at the same time it will help the system to maintain what the demonstrated trajectory was, right. It tried to reproduce the trajectory.
So, why don't we have the SK function in this proposed model?
Sorry?
Where is the SK function in this proposed model? HK term we have, right?
HK function?
This
so that was the firing of a Gaussian model. Yeah.
So, where is it in the proposed model?
Proposed model, it is sigma.
Okay, so it is a sigma. Okay.
So, it is just I have so it is HK basically, because I am also using a Gaussian mixture model here. I have changed it because to show that the system has some differences from the earlier, okay, but ideally they are same. So, now we design this component U as this, that it is a fuzzy rule based, right. So, you are familiar with fuzzy systems, right, TSK fuzzy systems there. So, my Lth rule is basically when x is GL, GL is the Lth Gaussian here. So, maybe when if L is 1, so basically when x is model 1, then what is the U? The system works in this way, right, it is reasoning based. And see here, the interesting thing about this model is, here we combine both the statistical learning and fuzzy TSK fuzzy logic. How? We learn this thing using Gaussian mixture model, that is a statistical model which is learned from expectation maximization, and this term U is learned using this fuzzy controller, and again the fuzzy sets are learned using expectation maximization, right. So, now this model has the capability to utilize advantages of both the statistical learning and fuzzy logic. So, we take cream portion of these two techniques and combine a better model, propose a better model. So, to first to find the Lyapunov function of the system, we propose this lemma. So, what we do here is to make the system stable, we need to find some B such that this one is alpha max is basically the maximum eigenvalue of this term. What is this term? This term is this, right. So, that is coming from the Lyapunov function analysis that I have already shown here using x dot equal to a x. And so, when we find P in this way where this condition is satisfied, well, you can say we have found the natural Lyapunov function of the system, because we are learning the system from the data, right, because this B and A we have learnt it from data. Now, this P we are also learning from the using this model. So, that means we are learning the natural Lyapunov function of the system. Now, we using that controller U will create quite less force to distort it from the expected trajectory, right. So, now how do we learn P? We learn it in a minimization problem where we minimize these two variables, where these two variables are defined as in this way. We search for Pi so that these constraints are met, right. So, we minimize this. When you minimize this, basically you see that gradually this function will go toward minimality, and it will come out like it will give you a P which will give the best Lyapunov function of the demonstration, right. So, this is done using this minimization problem is solved in genetic algorithm. In genetic algorithm we design the fitness function so that this constraints are met well while we minimize this two scalars, right. So, once we have that P, then we propose another theorem where we find that this K0 and K such that, and what this Ki and K0i is, it's from the definition of U, right, here. So, now our job is to find the controller from the data, right. So, for that this theorem is and see in this region L alpha, it is basically a region around origin where we make sure that no disturbance is working, so that we learn this K0 to nullify the effect of B0. So, in that way we learn this controller, and this again is learnt in genetic algorithm, and this is the proof. So, I will skip if well. So, now we have learnt one model which can reproduce the demonstrated motion, but you have already seen that we putting many constraints, we have actually learnt a conservative model, right. So, what happens with that model is when the motion is quite complex, that model does not work well because it was constrained. So, when there are many minute features in the trajectory, it simply overlooks that and tries to reach to the equilibrium point. So, that is why we try to relax that constraint. So, now suppose I will discuss about the idea behind relaxing this stability constraint. So, before that I will show how it works, that suppose M is a negative definite matrix, then and this is your Lyapunov function that we already showed, fine. So, now Fx this Mx will always be negative for x not equal to 0 as M is negative definite, and this term will be 0 when x is 0, right. But what if our M is not negative definite, not either it is positive, we cannot, we do not know what would be the Mx value is. But if we look at the state space and we plot the eigenvectors of this M, we see, suppose our M is a matrix such that it has two negative eigenvalues and one positive eigenvalue, right. So, this is the eigenvector, these back eigenvectors are corresponding to the negative eigenvalue, and red one is corresponding to the positive eigenvalue, right. And this area, it is basically the region of instability, in a sense that in this area Mx will always be positive and the rest part it will always be negative, right. So, now if we can formulate something that can help us to reduce this region, then we can say that in the global space our model has a big region of stability where that model can operate, and if we are able to operate our model in this region, right, in this blank region, then our model is always stable. So, that is the idea. To do that, first we do that we try to figure out what is the span of this region. So, and we calculate the angle, then we what we do, we formulate another lemma where we try to minimize, we try to minimize the span of this area, right. So, in that particular theorem what we do, we squeeze this region towards this positive eigenvector, and we try to maximize the area at the negative eigenvectors, right. So, that is the concept behind this theorem, and here ROO is basically the region of operation and ROD is the region of demonstration. So, we make sure that the demonstrated region is the region operation always remains inside the region of demonstration, and this is the proof of this theorem. I will skip that. Now, what you do, that model was learnt in a local area, right. So, it is not expected to perform in the global space. So, to make our system globally valid, what we do, suppose this is our demonstrated space, right, and this is our space of region of operation where the robot is actually being operated. So, we transfer this space to the demonstrated space, and we unfold the motion model, and then we again transfer it back to the original space and feed it to the robot. So, that is the concept, and in this way the region of or operation always remains inside the region of demonstration. These are few results. So, these are all experimental results. So, this is end effector trajectory, where this gray lines are basically the demonstration, right. So, I have shown the robot how to move inside the workspace from starting from this position to this, here black square is the target, and the blue one, that is reproduction of the motion model. Okay. See how it is working outside the region of demonstration. It's this results are with the model we first learned using precise constraint, the conservative model, right. Now, as I told you that this model does not work good when the features of the demonstration are complex. See, when this for this kind of trajectory, it could not learn it properly. So, it started from here and it could not capture this minute feature, and it came straight away and went to the target point. To tackle that, we propose that relaxed version of the model, and this is the result with that relaxed version of model. So, now you can see that the motion model has well captured this demonstrated trajectories, right. So, this is outside the demonstrated region. See how that is stable. See all the motions are stable. They are starting from here. The model makes sure that the trajectory reaches to the target point, right. And this is another one, right. And this is how the error is changing in the workspace. And this is about spatial scaling. So, we want a bigger trajectory than we showed, and it created like this using that transformation technique. Again, we created a smaller trajectory using that transformation technique. Well, so these are the summaries what we have learned. So, we have learnt a GMR maze model. We have shown that a GMR maze model can be learned while ensuring the stability of the motion model, and we have shown that locally demonstrated region, locally demonstrated motion profiles can be learned for a global perspective. Okay. And we have shown also seen that how the spatial scaling is applicable to this kind of model. Okay. So, that is how about this work. So, any doubt about any question and all for this work, then I will move to the next. Till now we have seen that how a particular type of demonstration have been learned in a single model. So, suppose I have shown this kind of trajectory here, and the model we have proposed, we have learned this trajectory. Now, for again another kind of motion, suppose this one, that model cannot produce this trajectory, right, because that is learned only for this kind of trajectory. So, now I have to learn another model to learn this trajectory. Now, in this approach we can combine in a single model this two type of motion. So, basically 2-3 kind of motions we can learn using the approach I am going to present, right. So, what is the motivation then? So, when you teach a robot, you want that robot to perform different kind of tasks, right. So, tasks involve different type of trajectories, like maybe one kind of this kind of trajectory, maybe another one kind of maybe of this kind, another maybe of this kind, right. And I want that a single motion model can produce this kind of this trajectories whichever I require. If I say the robot, well, I need this one now, or maybe from environmental information robot decides that now I have to generate this kind of motion. Well, then the scenario changes and robot decides that, well, this motion will not work, I have to go for this one. Okay. So, in this way robot needs many trajectories to work efficiently in the workspace. Okay. So, now here we define what is multitasking. We defined 3 category here. First is the robot is expected to go from A to B, and with a single kind of single type of trajectory, which is we name it single task trajectory, and single task trajectory, single task equilibrium. Then where for your robot starts from A to B and C to B with while executing this 2 type of trajectories. So, that is called multitask trajectory, single task equilibrium, and then again maybe the equilibrium point can also be changed, and while changing the trajectory. So, we term it as multitask trajectory, multitask equilibrium. Well, as of now we have defined our model in this way, right. So, now we have seen this model cannot incorporate any extra information. So, based on that we will decide which kind of trajectory needs to be generated. So, what we do, we introduce another parameter called xi here, that will basically a parameterization of this model, and it will help us to incorporate additional environmental information into the model, based on which the model will decide which motion needs to be presented here. Well, so now again the problem is about stability. When we learn this model blindly, it does not when you learn it blindly, it's the stability is not ensured. Then an external force would be required to maintain the stability, and it is also very obvious that the demonstrated trajectory would be distracted when we apply this external force, right. So, what we do, we apply an external force like this, and we ensure that this force also at the same line with this model, so that it has very negligible effect to as a disturbance to that model, rather it will concentrate more on the stability of the system. So, to do that, what we do, we try to figure out what is the energy dissipation rate in the demonstration, and we try to learn it, and we try to maintain it when the model is being executed, right. So, now we have a simple assumption here. Well, our energy dissipation rate, we abbreviate it as in terms of EDR, and it is given by this, where x is the state in position space, where x transpose x dot would give you the energy dissipation rate of the system. And we assume that this energy dissipation rates can be modeled using a weighted combination of local models, and where this beta is the map which will basically map the state space to the energy dissipation rate space, and we ensure that this kind of constraints are followed. I mean, constraint in a sense that beta will be learned such that the beta will always represent E dot will x is non-zero, and it will make sure that at x 0 beta is 0. Why? Because x 0 x equal to 0 is our target state. It is a generalized state, right. So, we can take equilibrium point as x equal to 0, and we make sure that at target point this beta, this thing is 0. Why? Because we do not want any change in the energy when it has already reached the target, as simple as that, right. Now, let us review what kind of motion profile can be there in the workspace in terms of energy changes in the system, right. So, now see here, robot end effector that starts from x 0 in the workspace in S1, then it enters in this brown region, that is called x 2, and then again S3 in this blue region, and reaches here to the equilibrium point. All the way along, see, the energy dissipation rate is negative. Why? Because in this state never goes beyond or overshooting this equilibrium point, always it is minimizing the distance to the equilibrium point. So, that means the energy dissipation rate is always negative, otherwise it could not have happened, right. So, that is one kind of motion profile that can be that is demonstrated. Another kind of demonstration can also be evident, that is, the state starts at x 0, well, it is moving and entering to the brown region S2, where that energy dissipation rate becomes positive, and it goes far away from the equilibrium point, then again it enters into the S3 region, and then it again starts going towards the equilibrium point. So, here changes is, here the equilibrium the EDR is negative, here it is positive, here again it is negative. So, analyzing the stability of this kind of systems is really very tough, especially finding a natural Lyapunov function to the system is very tough. So, that is why we do not use the previous approach where we tried to find the natural Lyapunov function of the system. And what we do, we propose a lemma that if we select our control input in this form, it makes sure that the executed model have energy dissipation rate similar what we have seen in the demonstration, right. So, if we use this control law in the model, and if we calculate the energy dissipation rate of the system, evolving system, you see that this Ex dot equal to beta, that is what we have learned from the demonstration. So, that means when you use this term in the control law, whatever energy dissipation rate during the demonstration we showed to the robot, that is maintained, right. So, our job, well, it is not done yet, but we have approached a bit, right. We have ensured that energy is decreasing at the same way, in the same way. Now, we will take one example to analyze the stability of the system, where we make use of non-monotonic Lyapunov function, where suppose this is your system, right, x dot equal to this is maybe your Ax, right. So, here it is a negative definite, but here you see that this is the plot of the Lyapunov function, right. So, this plot is when we select P is identity. So, Lyapunov the V, I mean the Lyapunov function value changes in this way. When we take P in this way, the function changes monotonically to 0, right. But in both the cases systems are stable, right, but here the V is not monotonous, whereas here V is monotonous, right. So, that means it depends on the parameter P how we select it, but this was again it is a very simple system. So, the finding Lyapunov function is very easy here, but the systems we are talking about, where we learn the system from the demonstration, they are not a simple, they are not simple systems, right. So, finding the parameter P is quite difficult. So, what to do, we take the approach of non-monotonic Lyapunov function, where we use this theorem that is proposed by Ritz in 1956, I believe. He says that, well, if you have a Lyapunov non-monotonic Lyapunov function and you check V, and if you can ensure that up to triple dot this term is negative, the system is stable. So, you find a P and make sure that this expression is negative, your job is done, right. So, that is about non-monotonic Lyapunov function, but see here it is taking triple dot. So, finding triple dot in a complex system is difficult. So, in 2002 or something, Amir Ali Ahmedi, he proposed that, well, we do not have to go up to 3 dots, it can be managed with 2 dots if we take 2 separate Lyapunov functions, right. We take 2 separate set of P's and we can find we can show that up to second dot, if it is negative, the system is stable, right. So, we use this thing and we propose this theorem that we defined our Lyapunov function is this term, like we take the energy as a V1 and another term which is x transpose P2 x dot as a second term, right. And so, here you see Ex is V1 and this is V2, and we propose this theorem where we find P2 such that this term is always negative, right. So, it is a scalar, positive scalar quantity, it basically defines the system's robustness. So, if we find this kind of system for a greater neta, then our system is more robust, right. So, sorry, any question? Okay. So, we find P2 here, you see that we do not have any constraint over P, right. We have this set of constraints and we do not have constraint any P, right. We have to make sure that this term is positive for all the demonstrated data and this term is negative, where we have learned beta using a nonlinear function approximation. So, this is the proof, I will skip again. Well, by searching those P2, we can ensure that the Lyapunov function is always negative within the WD region is basically the region where we demonstrated the robot how to perform tasks, right. Well, so again this approach makes sure that the system is stable within the region of demonstration, because we did not work outside the region of demonstration. But we want our robot to be stable outside the demonstrated region as well. So, we modify our control law in this way, which actually the effective control law becomes like this, right. See, now if follow this term is basically, as we have seen, when we used our first proposed law, here it was beta, right. Now, here it is minus e to the power minus alpha x transpose x. That means, if we use this u g outside the demonstrated region, the energy dissipation rate will be this, which is basically negative, right, and a negative energy dissipation rate will ensure the stability of the system. Well, our job is done. We can use our robot outside the region of demonstration, fine. So, this approach can be in this approach, especially we can use many function approximation techniques that we could not do in the first approach, only we used only GMR. Here first way I am showing how I use GMR to model this system. So, see, in the same way as I have shown that we have learned the FX using GMR, then EDR, that means the energy dissipation rate, that is we are achieving from the demonstration, we learn it using GMR like this, where as earlier they are the covariance matrices and these are the means, and we the cost function we minimize during the search of P is this, right. So, that is the log likelihood of the data set, where we minimize the negative of the log likelihood, and we fine tune the parameters of beta, right. And this is the algorithm where we learn the parameters. Theta b represent theta GMR beta basically represents the parameter of the beta function in the GMR based model. So, here this is my data set, I get the data set while presenting L demonstration. So, in the pre-training what we do, we basically learn the initial dynamics using the Gaussian mixture model, and we club all the tunable variable inside the parameter theta. Then during fine tuning, where we find P, we find all the theta hats such that P2 is existing in the model and the error simultaneously is minimizing. So, that is how we learn the GMR based model here. Okay. Then it is LWPR, okay, locally weighted projection regression, where the good thing about LWPR is it can learn functions of many dimension. What it does is it projects all the dimension in the reduced order dimension, where the model is well fit and it removes all redundant dimensions. And another good thing about here is it can be used for incremental learning. Suppose you have learnt a dynamics using for a set of parameters for a particular set of demonstration. Again, after some days you feel like, well, I need another kind of motion. So, you can use that particular model you have already learned, and again you take another set of data and you can incrementally learn the new dynamics. So, that is the good about LWPR, where beta is represented like this. So, these are the projections here, and the weight is defined by this. You see again here it is a Gaussian function where dk is the distance matrix. So, LWPR also works in this way, where this local models are learned, right. So, we have k beta numbers of local models here, fine, and these are the basically centers here, Ck and dk is the distance between the centers. So, here in Gaussian mixture our shape was like this, but in LWPR they are circular, because we have a diagonal D matrix, right. And in LWPR we minimize this cost function, right. So, it is we maintain that this cost is minimized, while this constraints that we have set in our theorem is minimized, right. And this is the algorithm for learning motion in LWPR, where we in the pre-training we learn from the data set the model, and then we club all the so basically here what we are doing is we are changing the distance matrix D of the local models, and based on that we are finding the centers of the local models, and we finding supporting parameters that will feed the data better, right. And once the data is fit, then we go for the fine tuning, where we learn the Lyapunov P matrix. So, that is P2, again that there is no constraint on P2, like it has to be positive definite, it has to be negative, nothing, because we have already set our Lyapunov function in that way, such that we do not have to put any constraint on P2, right. Well, this is one human expert is showing how this thing is how a pick and place task is performed to the robot. So, here it is there are many objects inside the store, and this person the kinesthetically demonstrate how to reach to the object and grab it and place it inside the bin, and this is how it is executed. I'll then again I'll show one video. So, it is the demonstration. I have only shown here one demonstration, but I have showed actually 10 such demonstrations, and from that I learned that model. So, this is one demonstration where the robot goes there and grabs that product and place it inside the rack, where when it is placed it comes out. So, now I learned the models using GMR that I have already described, and now the robot will execute that task. See. So, the robot actually learns here from there to here the end effector trajectory, right, and grasping is separately done, it is not part of the learning. Okay. So, it learned basically 3 motions. So, this is the plots where first I plot the monotonic state energy, where the end effector starts from here and monotonously goes to the target this black star, where you see that here this is the energy dissipation rate, right. So, here you see it is always negative. Okay. This is one kind of motion. Then again in the next you see that here it went to it has a positive overshoot, right. The energy dissipation rate was positive in this region. So, especially in this region. So, these are basically the 3 models are there, where red one is the demonstration, and we here GMR based model, LWPR based model, and SVR based model are there. Now, here it is the multitasking. So, one task profile is like this, another one is like this. These are the starting position, and this is the target, and this is its energy profile. So, here this green and this blue one is basically the reproduced, and green one and the other one is 2 tasks represented here, green and black, green and red, sorry. Okay. So, this is one multitasking, where the equilibrium point is, so that is basically multitask single equilibrium trajectory, and that is with the previous one was with GMR based model. So, that is with LWPA, so, and this one is with SVR, support vector regression. Okay. So, SVR for this it was the model was not well learned, so that is why this here the model was quite faster, the energy dissipation rate was far negative than the expected one, and it reached faster to the target, but it was not intended because of the model was not properly learned. 5 minutes? Okay, I thought it's up to 3:30, right? Okay, fine, then I'll okay, it's okay. Well, this chapter is finished, so another one is about application, so I can directly okay. So, these are the another motion profile where I have two equilibrium points, right. So, multitask multi equilibrium trajectories, right. Okay. This is comparison how LWPA in SVR works among the algorithm. This is a and this summary. Well, I am going to the next chapter, right, where we learn how to a pick and place task works. So, this is the scenario of the warehouse where the intention is to replace this human using that robot. So, basically the intention is that making that person jobless, right. So, we have the task at our hand is perception model, where we have to perceive what the object is, we have to recognize what is the object, and this is the motion planning and grasping model, where the robot will do the motion planning stuff using the learned dynamics that we have taught it, right, and then it has to grasp the thing, right, and this is a workspace. You have already visited our lab, right. So, it used to look like this. So, camera was not there, so we could not show you the demo, and we learn here, we learn, see here during the pick and place task, we earlier we have we only showed that how the position of that end effector can be learned, but here see during the pick task the orientation of the end effector is also very important, right. So, we need to learn how the orientation profile are changing in the workspace. So, here the we learn it using the previous model, but here we incorporate position also. So, now our state space is 6 dimensional, earlier it was 3 dimensional, right, and we use that fuzzy control law here that we have already discussed, and the quaternion error, which is position state, is basically the error state, that is the desired position, and that is current position. So, different any question?
So, you are developing those equations, governing equations.
Yeah.
How that is coming?
Sorry, I didn't get which
How
one.
you are getting? Yeah, this is like the 65 equations. This governing equations you got. This is the equation which ultimately you will implement in algorithm.
My
So
in
how you are getting these equations?
see, this is some form, right. So, this is a linear systems form. If you just consider this part, right, this is a bias part, this is the system matrix, this is your input, right. Now, this is, if you consider, forget these things now, if you consider this represents a linear model, a linear system, right. So, now what we do is we take the weighted combination of the linear models and say that this is our nonlinear model, and this is nonlinear in a sense that these values will be changed because of this fire in. How the system will be fired based on the nonlinear function, maybe the Gaussian function we are using here. So, based on that, the system dynamics will be changing at each instant in the state space, right, and our job is to find out what the value of this b k's, a k's and k i's and k zeros, right. So, that is our algorithm, basically finding out these parameters and the parameters inside it.
You will decompose that further.
No, It's the algorithm is searching such that this model gives the best fit with the demonstration.
Which is the values of A, B, and U for every causing instance.
Exactly. Suppose, do I have how?
We don't have time because
We don't have. Okay, I'll talk to you later. Fine.
you can talk to him later.
Okay. So this is our the orientation error. How we this is our orientation state, right? And this is a position state. And the training and execution, where this is our data set, right? And this is our make the training data set in this way. Then the new, after learning, the new X state is basically the current, I mean previous plus the sampling time into the dot of the. So Euler, just Euler approximation we are using here, and this is that is how we get our new state, new position. And this is the task flow where we first we learn the model, then we during the execution we check what is the current state, we take the goal state and we unfold the model, and the x dot gives the new position or orientation, right? And so that is the task we want to achieve. So that is how it goes from here to the tote first, then during the placing it here. So here we are learning two types of thrust trajectories, right? So and the recognition is done using the convolutional and deep neural networks, that is VGG 16 called, it is called VGG 16. So that is standard, that is not proposed, so you can find it in internet. And the more recognition model gives output like this, it creates a bounding volume around the object, and we take the we calculate what is the grasping position based on the this what it is called this region of I mean ROI basically, right? So and this is the response of this, this is orientation response, this that is position responsive. Once this is for picking and this is for when it is keeping the object, right? So this is at each individual trajectory. Okay, so I'll directly show the video, right? I guess this one. See now first it's looking the camera is looking over here, it's recognizing the object and have collected the position, and the robot first moved here, the suction starts, the object is grabbed, now this motion, first straight then this. Okay. The interesting part is the demonstration was provided not with this robot, but that robot first I showed. So, I demonstrated in other robot and executed the planner on the other. Okay. Okay, that is how it is. Okay, I am done. So, these are the profiles I have already shown, this is summary. Okay, thank you.